Today I want to talk to you about taking JavaScript to the edge. So the vast amount of choices that we have in modern IoT is crazy compared to what we might have had 5-10 years ago. You know, you've got choices of devices, hardware attachments, you've got languages, deployment mechanisms, different deployment mechanisms and frameworks. And I'm going to try and demonstrate all of the different options that you do have and how we can then use these to deploy JavaScript to edge devices. So, choices. Firstly, you need to decide which device are you going to run your code on. Now, in the past, you may have only had the option of a few small system on chips or a couple of microcontrollers. You might have had a very restrictive set of development and debugging tools. You know, maybe they only run on Windows or OS X or Linux. Architecture, you might not be able to control that, just whatever you had at the time. Fortunately, this isn't the case anymore. So, here is a subset of single board computers that Resin currently supports. You can use any of these in any project that you'd like. We've got the Raspberry Pi and the Raspberry Pi Zero. These have got different architectures, different clock speeds, different price points, and basically you pick what works best for you. You know, you've got the Raspberry Pis, they've got USB, they've got HDMI, everything you'd expect. We've got the Intel NUC, these are x86. They've got all of the I/O that you would expect on a normal computer, albeit less. We have the NVIDIA TX1 and they've also got the TX2. These are designed for doing machine learning at the edge. You've got the Raspberry Pi costing about £30, the Pi Zero costing around £10, the TX2 costing around £300, £400. So again, it depends what you're after and what you're looking for, but the point being you've got a choice for what works best for you. So this gives you a blank canvas on which to build, and maybe if you chose the Raspberry Pi, your device is designed to have some swappable hardware or hats or additional hardware. So we've got hats for the Raspberry Pi, which stands for hardware attached on top. Love the name, by the way. On the left, we've got the Sense hat. This was designed for the AstroPi project, which aimed at getting contributors' code in outer space. And this hat was sent to the International Space Station with some code by members of the public. We've got a speaker hat. This means that if you want your device to be able to make noise, play music, that kind of thing, that's easy. You put it straight on the GPIO header. We've got a motor controller. That means any DC motor, you can supply some power and then use the Raspberry Pi to control those motors. We've even got a high-def touchscreen that you can put onto something in the size of the palm of your hand. So these are examples of different kind of inputs and outputs that you can very easily add to your IoT project with the minimal of installation and setup. And often there's libraries already available, everything's ready to go. So you've chosen your device, you've chosen the additional hardware that you want to add on, all of your sensors, all of your output mechanisms, that kind of thing. Now, how are you going to deploy that code to your device? So with modern IoT deployment, there wasn't really that many options. So being from Resin, I'm going to talk about how we have enabled IoT projects to deploy their code to their devices. Containers. Containers are great. So containers are a way of packaging up all of your code and your dependencies and putting them into an environment which, when you run them, will be exactly the same. You can make sure that your target can download, can run, can clean up after your code without knowing a single thing about your application itself. These containers are created from images, which are a set of layers building on top of one another to define the environment in which your code should run. So I'm going to talk a little bit about how we make those images and then how we get those onto devices. So, images, set of layers, just like this rock balancing. Thankfully, it's a bit easier than that. So you start out with what's known as a from line. So, sorry, this is a Docker file. and a Docker file you use to define the image that you want to build. They have a set of commands, each one being a line, and each command in the Docker file will produce a new image, which is the image before it plus whatever additions that command has added. So generally the first command that you add is a from line. What this says is use an existing image as a base on which to work from, and this is known as a base image, as you might imagine. So what we're saying here is take the image, resin/Raspberry Pi 3 node, and build upon it. Now this image was created by Resin to run on the Raspberry Pi. It's a Debian environment. It has Node pre-installed, NPM pre-installed, and it's the bare minimum that you need to deploy a JavaScript application. Next, we've got a run command. So this run command, what this says is take my base image, run apt-get update, so run the Debian package manager and decide what packages are available. And then we're going to install curl and alsa. Let's say that these are dependencies of your application. You know, maybe you're going to do some downloading of music and then playing it. So what we've done here is we've taken the base image, we've added another layer, which says I've got the Debian base image with curl and alsa on top, and that's it. So what we need to do next is copy our application or our application source code into our image. So we've used the workdir command. What that is it says every command that I run from this point on should be in the working directory, and in this case I've chosen USR source app. You can think of this as equivalent to doing cd USR source app in your shell and then running some commands. It's running in that directory. After that, I've taken a copy command, and this copy command says in the current directory there is a directory called source. In that directory there's my source files. I want to take those source files and add them to the working directory of this image. So each line is creating a new image. The workdir line would create an image that's got the Debian node image. It's got curl and alsa. It's got some metadata to say that the working directory of this image is USR source app. And then there's another image that is built on top of that, which says all of my source code is in that working directory. So now we need to define which code is going to be ran when we turn this image into a container. For this, we use the cmd command. Cmd command says, when we take this image and convert it into a container, what should happen when we start that container? What should be done? So this says, I've got an image. When this image is turned into a container and it's run, it should take the app.js file that we added in the previous copy step, and it should run it with Node. So simple as that. Okay, so we've got an image. How would we then deploy it to our device? I'm going to kind of rush through this a little bit because I'm not talking about Resin, I'm talking about JavaScript. So you would create an application on the Resin dashboard and download the Resin OS image for your device. Resin OS is an operating system that we've created specifically for devices which have a thin host OS. They run exactly what you need and nothing more, and your user container will go on top of that, and that's all you need. That's Resin OS. It will connect to our dashboard and handle all of that. So this would be how you do that, but that's irrelevant. You would install the Resin CLI. Again, if you want more information on this, we can look at the documentation, but in general, you just install the Resin CLI. You do a Resin login, which would take your application, your user account, and associate it with your local instance of Resin CLI. Now, here comes the magic. So we would use Resin push. So you would do Resin push and then whatever your application name is. This would take your current directory, which includes your Docker file. It includes your source code. It would package it up and it would send it away to our cloud build servers. Our cloud build servers come in different architectures. So we've got x86, we've got AArch64, we've got ARM v7, anything that you can deploy to, we've got a native cloud builder ready there to build your code into an image. So you've sent your code to our builders, it's built successfully, hopefully, and this then gets sent to what's called a registry. The registry is a server in the cloud that holds a lot of images. And you ask for an image by name, it checks if you have access, and you download it. So we've got that, and it's been installed. But why would we want containers? Why are containers a good thing for IoT deployment? Now, at first glance, it might seem, we've done a lot of all this work, but what has it given us? Why is this something that we want to do? So let's talk about the benefits of container-based deployment in an IoT setting. Isolation. So first, isolation. So when you're writing code for an IoT device, often it can be a lot more complex than your typical desktop application. Often you need to have it a lot closer to the host operating system, a lot closer to the hardware on the device on which you're running. You might need to interface with the networking or, again, specific hardware. Isolation allows you to draw a line around your user application and say, this is allowed to do this specific set of tasks. If something goes wrong in those tasks, we get rid of that container and we start again. What that means is your host operating system cannot be affected with a container that's acting badly unless you configure it seriously wrong. What this means in the IoT setting is you don't brick devices. So if you imagine you've deployed an IoT device to something in the middle of the sea, in the middle of the Atlantic Ocean, if that device suddenly goes offline, there is nothing you can do other than send somebody to go and either fix it or recover it, and that's not an easy task. If we use containers and something goes wrong, we tear down that container and we start again, and the device is fine, it's pristine. Reproducibility. So when you're using containers, you have an environment in which your code runs, and that environment is the same on your device. It's the same on your local dev environment. It's the same on your testing infrastructure. It's the same everywhere. So if you discover a bug in your code, you can reproduce that bug locally and fix it locally. And in the setting of IoT, security is a massive thing. These devices are in people's homes, they're running machines, they're everywhere. Security is a big thing. If you see a security problem, you need to fix that security problem then and there. And being able to reproduce and fix locally is brilliant. Application delivery, I think personally, is the most important part of using containers for IoT. So for a typical desktop application, you've got several different methods of deploying it. You've got auto updaters, you've got web apps, you've got, at a push, you've got FTP if you need to. But if you have an IoT project and that device is not on the same local network that you are, your options are pretty limited. We need some way of telling the device that the update is ready. We need some way of the device downloading the application without knowing anything about the application itself. And we need a method of tearing down that application should something go wrong. Now, Docker containers enable you to get all of these things for free. This is what Docker was designed for, and this is what Docker does very, very well. Also, if you have a container and you push an update, you've got a device out in the field that's got a 2G connection. We're talking, 2-3 kilobytes a second. What you can do is say, okay, I have this container and I need to move to this container. We can work out what the difference between these containers is. We call it a delta. Just download that delta on the device and apply it to the container that the device has. This means we move from container A to container B with the absolute bare minimum of data transferred. So, we've chosen our device, we've chosen our additional hardware, we've chosen our deployment mechanism. Now we need to choose our software stack, and we're at a JavaScript meetup, so let's assume that we all want to use JavaScript because we all know and love it, hopefully. So, why would we want to use JavaScript at the edge? That is an interesting question. There are a lot of programmers that know JavaScript. Using the Stack Overflow developer survey from 2018, 70% of respondents use JavaScript. 17% use TypeScript, which is a superset of JavaScript. And whilst it has typically been a language to use to create web applications, in recent years it's definitely proved itself to be an extremely competent and useful general purpose library. Allowing JavaScript to be run at the edge means that we can take all of this knowledge, in which 70% of programmers are already familiar with, and apply it to a complete whole new set of problems. We have a gigantic existing ecosystem of packages for JavaScript. I took this graph from modulecounts.com today. We've got, a lot of popular package managers at the bottom, and then far and away at the top, we've got NPM with, 500,000 packages at the start of September, and now in July at 450 plus packages a day. It's got a lot. The beauty of this is that these can be used in an IoT setting with zero changes in general. Normally. So the next point doesn't just apply to JavaScript, but applies to higher level and more modern languages in general. So in the past, for embedded devices, it would have been originally written in C or C++, or at a push, even assembly. Partially this was because we'd need to squeeze every single CPU cycle or every single byte out of memory. Now we've got single board computers which run at gigahertz. They've got gigs of RAM. This just isn't that much of a problem anymore. And programmers will prefer to use languages that aid maintainability and ease of use, ease of debugging, rather than getting that raw performance. And I think that's why JavaScript has been used on the edge so much already, and why I think it will continue to do so. So, what does JavaScript at the edge actually look like? Surely it's got to be different. Hopefully not. It should be exactly the same because it's JavaScript. It runs on the Node engine. It has the same data models. It has the same behavior. So you can write code for the Node engine on your desktop, and it should behave exactly the same to code that you run on your device, ignoring any hardware differences. Maybe you're simulating some hardware. Your test suite should be just as effective when you've run it locally to when you've run it on your device. And your Node modules should be installable both locally and both on your device, and they will behave in exactly the same way. So I want to show you how well JavaScript can lend itself to edge programming. So this snippet of code is from a Node library created by Resin to interface with the sense hat that I was talking about earlier. It takes a handle to the LED matrix, chooses an X or Y, sets a pixel. Pretty standard JavaScript, we've all seen this. It's pretty standard. It's not special in any way. You wouldn't be surprised if you see this on some web application. It doesn't change at all. So what about using the sensors? Because the sense hat has a lot of sensors. Surely it's going to be a bit hard to use them. Nope, we've got exactly the same JavaScript that you'd find in any other web application. It's pretty standard. You create a handle for the IMU, also known as the inertial measurement unit. Request the sensor data and provide a callback. Again, standard JavaScript. You'd see this anywhere. This is typical. Doing something extremely non-typical for JavaScript, and it just works. It just does exactly what it's supposed to do. We've got the same JavaScript objects. They're passed to json.stringify. We've got the same error handling as a normal Node callback would. It just works. Even hardware events are made extremely easy. So I'm sure everyone's familiar with a JavaScript event emitter, so what you would do in this case, you would ask for a handle to the joystick. You would set up callbacks for joystick events. So in this case, we've got press, release, and hold. And this is, again, very, very typical JavaScript. And this is running on a device out on the edge. So we've chosen our device. We've chosen our additional hardware deployment mechanism. We've chosen our software stack. The only thing left to do for you guys to write some code. So one of the beautiful things about containers is you often make a distinction between application state and application data. Anything that needs to be kept should go in application data, and how we actually do that at Resin is what's known as Docker volumes. And these are just segmented parts of the file system which can hold data. Application state, on the other hand, would be lost. So you would design your program in a way that if it needs to recover and go back to a certain point, you would read application data. Now this is nice because it means that if you have a bug in your code that would change your application state in a weird way, if you tear it down and bring it back again and it works going from data to state, then it should work fine. This is JavaScript at the Edge, and I hope it was very informative.